All right, so this is joint work with Matt Ollis from Emerson College. We've started working on this project almost 4 years ago. And initially it was going slow, but it started becoming very fruitful recently. Because again, I'm aware that I'm talking mostly to non-specialists. I'm including a little bit of background at the beginning, but I'll try to keep it short so we can actually come to the more interesting parts as quickly as possible. All right, so let's start. I'll start with the basics, but very briefly. The definition of a graph. The graph has vertices and edges. Graphs in our case are always going to be discrete objects. So if our graph is finite, then the indexing is going to be through the natural numbers. I'm sorry, infinite. But mostly our graphs are going to be finite. And in that case, the indexing is going to be through this notation that I'm using is for the first V elements of the natural numbers. I wanted it to be parallel to the cyclic group CV notation. Then the edges come from the set that I denote as PV. I called it PV because these are unordered pairs of vertices. So edges are going to be any from the collection of unordered pair of vertices. This is an example. By the way, the next 11 slides are going to have the same format so that we can all ease into the subject. They will all have something at the top and an example graph and some observations about the example graph. Our graphs are going to be simple, meaning there aren't going to be any loops, undirected, so our edges are not going to be having any directions assigned to them. But one thing we will do a lot is we will do vertex labeling because it makes our life easier, and of course the conjecture is also defined through that. And once I do the labeling, I will often abuse the notation, right? Instead of referring to this as the vertex V0, I'll just directly refer to it as the zero vertex. I don't think that's going to be confusing to anyone. All right. The important type of graph that is relevant for the Buratti-Horak-Rosa conjecture is the complete graph. And the complete graph is basically when the set of edges is the entire set of ordered pairs. So any two pairs of vertices are going to be connected. So you have all the vertices and all the edges that you can have. And once again, we'll do identifications. And here I'm already starting to move beyond because it's more interesting for us from the perspective of the conjecture to think of our labelings not within natural numbers, not within the first V elements of natural numbers, but more in that group ZV. In fact, once you actually really do identify, there's going to be a connection to Cayley graphs, but we're going to get there in a moment. Circulant graphs, you can think of them as sort of the partial subsets kind of, or partial subgraphs of complete graphs. The important thing about circulant graphs is that they are cyclically symmetric. Basically, if you rotate this graph and if you change the roles of 0 and 1 or 1 and 2 and so on, the graph stays the same. That's because we have a connection set given to us and all the elements are connected via that connection set. So all the elements locally, the picture looks the same everywhere. And once again, we're doing that vertex labeling. So we're already starting to think of these as almost like the elements of Z7 in this particular case. And that brings us to this one, the labeled circulant graph, where we actually just say, okay, forget about it even through the lens of labeling. Just say that your V is ZV. When your V is ZV, let me go back for a moment. Instead of having to define how my edges are going to be through these indices, I can actually define it directly additively. So instead of doing that entire thing via indices, we just cut the middleman and then do it via the additive aspects of the cyclical group CV anyway. All right, next graph that's going to be important is the Cayley graph. Cayley graph is the graph of a group with a generating set. But if you look at the definition, you can see that it's actually very similar to what I was, again, let me go back for a second, what I was calling the labeled circulant graph. We again have the edges given to us by differences that are defined via this connection set. And in this case, instead of the connection set, we have the generating set. And because of that, of course, there is this connection between the two. Basically, the labeled connected circulant graph is a Cayley graph where the group is Zn, which is why, oh, this is a typo. I should have called it ZV. Every now and then I, of course, go back to the algebraic notation, but we prefer to use the V for the total number of vertices in this context. So just assume this is ZV. And there's one other type of graph that I should be defining, and that type of graph is the cycle graph. And the cycle graph is when either in the Cayley graph or in the labeled connected circulant graph, our generating set or the connecting set has only one element, and that's the element 1. So you end up getting this perfect cycle. So all these different views are going to be important in the context of defining the Buratti-Horak-Rosa conjecture. So here is what the conjecture is. Well, again, I'm saying here is what the conjecture is, but I'll actually give you multiple different equivalent versions, okay? The simplest way for a mathematician to think of it is just listing all elements in the cyclic group of order B with a given multiset of V minus 1 minimal cyclic step lengths. So what does that mean? For instance, in the example, they say, we're in Z7, list the elements of Z7 using 2 step lengths of size 1, 3 of 2, and 1 of 3. So that gives us this multiset, and multiset, of course, is a set with multiplicity. And I'll immediately start abusing the notation. I won't bother with these bars because they'll just make everything cluttered. For simplicity of notation, I'll ignore the bars immediately. And then I'll denote the multiplicities exponentially instead of, as coefficients, because this is neater and easier to follow. So one such list that we can come up with is 1 second, let me move this to the side, is this list. And let's look at it. Let's see what's happening. From 0 to 2, I have a step length of 2. So I used 1 step length of 2. 2 to 3, 1. 3 to 1 is again 2. This step is important, right? Because we are thinking of things cyclically. Of course, from 1 to 5, we think of that as a step of size 3 and not size 4. And this distinction, as elementary as it is, of course, becomes important later on in our constructions. 5 to 6, we think of it as a step of size 1, and 6 to 4 is a step of size 2. So overall, we do end up getting 2 steps of size 1, and 3 of 2, and 1 of 3. All right, so here is another way of thinking about this equivalently. Now, this is not useful for basically manipulations, okay? So from our perspective as the people writing the papers, this is not very useful. On the other hand, it is useful to be able to describe this to even non-mathematicians. If you think of the problem through chains linking all the vertices, this could be easily described to a non-mathematician as like thinking like a circular ring of maybe like a train line. And then you have your train itinerary, and you want to be able to visit each stop, each train stop, only once. And someone tells you the multiset, meaning that you want your trips, or 2 of them, to be only of length 1. 3 of your trips should be length 2, and 1 trip should be length 3. Can you, using those trip lengths, travel all the stations, visiting them all once? This is, of course, again, as I said, easy to describe to non-mathematicians. Another way you can think of this is if any of you are interested in music, in particular in this case because we have 7, so you can think of that as the 7 notes of the diatonic. But for other V's, this works also. You can think of this as like coming up with a melody, and with note step lengths in between each notes, like move up by a second, by a third kind of thing. So again, this is useful for describing it to people outside the math, and it also shows that there can be some practical real life applications of this problem in various fields of engineering and such. This description I'm not only including because I'm aware that there are analysts in the group, so I'm paying homage by putting nth-roots of unity. It's also important for something that I'll observe later. But this is directly tied to, of course, the previous photo. So instead of thinking of this as a cycle graph, think of them as the roots of unity. And then describe your trips now, not as trips, but as these like arcs or the paths, arc paths, if you want to call them. And, each of them are basically sizes of multiples of an nth slice of the circle. The problem then can become described exactly the same way to non-mathematicians that way. Moving on to the view that is more important from the graph theory perspective, this is the view where we think of it as finding Hamiltonian paths in the complete graph. In the complete graph with, given multiset of V minus 1 cyclic edge length. So cyclic edge length again ensures that from 1 to 5, I see this as edge length of 3, not edge length of 4. And then, of course, the path that we were describing moments ago as like going around in either the cycle or the circle. Now we're actually thinking of them as paths within the graph, but of course, it's an equivalent problem. We get a path. The path in this case is of course, the list is the same as the previous list. Now the list is just representing a path, 0 to 2, 2 to 3, and so on and so forth. Now, immediately I'll add in new definitions. One definition that we will add is the definition of support of a multiset, which is, of course, also oftentimes referred to as the underlying set. And that is, of course, the set where all the multiplicities are removed. So in particular, if someone gives me a multiset with 2 1-steps, 3 2-steps, and 1 3-step, one of the first things that I actually consider is forget about the multiplicities, what type of steps that I have. I have a step of type 1, step of type 2 or length 2, step of length 3, and that becomes actually important, and we'll actually see immediately in the next view why that is important. In the next view, we can define the problem equivalently using circulant graphs this time. Now, for this one, I picked a different example. Let me go back for a second, because in my example, this multiset actually uses all types of edges. In Z7, there is no edge length of 4. 4s are, of course, reduced to 3s. So by virtue of putting 1, 2, and 3, I'm using them all. But what if they had given me one that's not using 3 edges, as we call them? An L edge is an edge with length L. So in that case, I don't really need to consider the problem in the complete graph anymore. Instead of the complete graph, I can reduce my attention to only the circulant graph that is defined by those given edge lengths. So for instance, if the multiset doesn't include a 3-edge, an edge of length 3, then I don't need to think about the K7 anymore. I just think about the circulant 7 with 1 and 2. And look for my pattern here. This actually becomes rather critical, as we will see in a moment, because this is one of the topological connections leads from this circulant view. All right, moving on to yet another equivalent view. And this is, of course, coming from the fact that a circulant graph is a Cayley graph where the group is the cyclic group of order, again, B in this particular case. So then we can think of this as finding Hamiltonian paths in Cayley graphs. And if you find one Hamiltonian path, as we were describing moments ago, because the circulant, and hence in this particular case, the circulant that is itself a Cayley graph, is going to have this cyclic symmetry, I can then rotate it around or translate it, incrementally. And instead of starting at 0, and I can start at 1 and mimic the same pattern, and that will give me another Hamiltonian path. And these translations will in return provide, what is called a graph decomposition of the Cayley graph. And this becomes then the connection of this problem to the problem of graph decompositions, which is, again, one of the applications to it, through computer science, for instance. So we've already seen that it can be used to, attack some problems in various engineering contexts. And here we're seeing that it can also be applied to computer science. All right, these are all the different equivalent ways of thinking about the problem. Now let's formally describe the problem. Marco Buratti came up with the conjecture in 2007. He is a very prolific person in graph theory topics of this kind, decompositions and such. But he himself actually never worked on the problem. This is one problem where he described it, but he didn't work on it. And when he described it, he was mainly thinking about the prime context. In the prime context, the conjecture is that, yes, given any multiset, we'll be able to find the Hamiltonian path with those cyclic edge lengths. And so far, all the inspections that everyone has done seems to indicate that the intuition is that the conjecture is true. In fact, we find an overabundance of paths every time we look at a specific case, but it becomes very difficult to describe it in the general context. Later, this will move down to C. Don't be alarmed. There is a B in the middle that's coming. Later, Peter Horak and Alexander Rosa in 2009 reformulated this for general V, where V is not prime. And then Anita Pazzotti and Marco Pellegrini, who I believe is listening to the talk right now, have reformulated it. They also are actually the ones that have highlighted the connection of this problem to the graph decomposition problem, I think combined with maybe Simon and Stevens. In this particular case, if V is not prime, then there is a condition. Not all Hamiltonian paths are realizable, as we call them. The realization is, when a path realizes a multiset. They are not all realizable because if you have a divisor of V, then of course using steps only via this divisor, you will never be able to move to, let's call them cosets, right? So you'll never be able to move to the other cosets. So the divisor D of V will have D different cosets that need to be bridged by a step of a different type. And that will, of course, mean D minus 1 steps of that type. So only the rest of them, which would be V minus D of them, can be of this type. There needs to be D minus 1 that are connecting those cosets. That coset view is going to become important, and I'll show that to you visually also. And the third step is something that Matt and I have described in our second paper on the topic, which we submitted maybe in December. And it is the case where V doesn't have to be prime, but everything is coprime. So things work as if V is prime. And in that case, any Hamiltonian, any multiset is realizable. All right, so I will now show you some of the known results on this, but I will not dwell on them too much. I will not describe them each individually. Instead, I'll highlight why the problem seems to be a daunting problem. Now, when U is 1, the problem is trivial. If if that element is a generating element of your group, then it generates it. You just take that element, repeat, you cover all the group. But if it's not a generating element, then it fails. It doesn't work. So it, in that sense, is trivial. The U is equal to 2 case for prime was actually independently solved by these two pair of scholars. The reason why Dinitz and Yaniszewski didn't do the non-prime was because at that time the problem was only described for prime. Horak and Rosa, in the same paper that they solved prime independently, also described it for all V, and for U is equal to 2, they also solved it. But the moment we hit, not U, of course, the size of U is what I mean. The moment we hit the size of the underlying set being 3, things start getting ugly. You have to make a choice. Either you pick specific examples, and in those cases, those specific examples, you can solve them. In fact, recently, my collaborator Matt, with a student of his, Pranit, did this for a bunch of them, where the maximum element in the U as long as it's not greater than 7, they have resolved it. Of course, they did it computationally, but still, it is doable. If you want to have your underlying set in a more general form, that is also somewhat doable, but then you get lots of very, ugly and complicated conditions. Some of them are useful, but often it is not immediately obvious how they would be useful. When u is greater than 3, the problem is complicated even more. Again, for specific ones, we can come up with results with underlying sets with some very variable format in them. Then you have either restrictions or you have lots of conditions. Now, one thing that you might, there is one, before I say that, there is one example where we have lots of results, but that's because Brandon McKay and Tim Peters did this via computer search. So, if you want to come up with a systematic way of attacking the problem, it's challenging. One thing you will notice is that a lot of these underlying sets that I've shown you in the past slides, let me go back a little bit, have ones in them. This is not very surprising in the coprime case or in the prime case. If you have a 3-element multiset, you can do a group automorphism, basically a multiplication in ZV, and via that automorphism, send one of the elements to 1 and rewrite your underlying set in terms of 1 and 2 other elements, which is why a lot of the focus had been, and so was ours, by the way, on multisets where there are many ones. In fact, in the literature, it had been appearing like the difficulties were going to be in one direction, but Matt and I actually have shown that the difficulties in at least for underlying sets of size 3 might be in the other direction, but I think I'm just gonna skip that for time purposes. All right, so in 2003 we started announcing our results after working on this problem for a couple of years. And then we started submitting them into journals starting with 2004. We've submitted 3 papers so far. Another one is in the works. I will dedicate a good chunk of our talk to the results that we submitted in 2023 already, although we have actually come up with many more recent results. But I want to talk about this so that we can get used to the problem. And then towards the end, briefly, I'll tell you what some of our new results are. Basically, in our first paper, we had these 2 results where we said if V is large enough, in these 2 particular forms of underlying sets, we get the problem resolved. There is a caveat in the second one, but in the top one there is no caveat. It is honestly, if it is this form and V is large enough, then the BHR conjecture holds. And this was significant because for the first time in this problem, for underlying sets of size 3 or more, we were able to show this for infinitely many underlying sets for which there are infinitely many values of V. So we had infinitely many in both the sense of the types of underlying sets and the types or the values of V. This was something that was elusive before. And we're hoping to this day, and our results that we're building after that are also indicating a possibility that this could be a first step towards solutions for infinitely many U. And similar techniques provide many partial families, but I will not, of course, clutter our conversation with those. I will mainly talk about the methods that led to the top result, not even the second one. The second one and the methods that we use there have also led to other future results or other results in other papers of ours, but I will talk about this and what it led to instead. And if you take these and if you combine them, especially for the top one, you also get some partial results for when U is strictly greater than 3 or the size of U. But again, I won't bother you with that. Instead, I'll talk about the realizations that lead to those results and how that result looks and then the tools that build up for it. So one of the reasons why we think anyone who has worked on the problem, although it's very hard to make headway into it, why all of us think that the conjecture should be true is because once you find a realization, it actually gives rise to many others. Okay, so if you have a path that you achieve using your multiset, then you can actually manipulate this very easily. One thing is you can do it reverse. So instead of starting from 0 and finding yourself at the end at 4, start from 4 and find yourself at the end at 0. Now, that is, of course, a cheap way of coming up with a new path because even visually, it doesn't really represent a different set as a path, right? But then there is the complement. If you take all the indices or all the elements, and if you take their complements with respect to the size of your group, so 0 moves to 6, 2 moves to 4, basically like 6 minus whatever the index was, you get another pattern. That's the complement. Then you can take the complement of the reverse or the reverse of the complement. Luckily, they are the same, but it gives you another type of path. And moreover, as we described, there are these translations. So instead of starting my path at 0 and moving to 2, if I start at 1 and move to 3 and continue the pattern that way, that gives me another path. In fact, for each path translations, because I'm in K7, will give me a total of 7 paths, 6 translations than the original one, and 4 categories. So there are, as you can see in the next slide, there are 28 paths that you get once you find one path. Now, I'll talk a little bit about this. I don't want to belabor the point, but with the red numbers here, I'm listing what the directed edge labels will be. As you can see, the edge labels themselves are not directed from the multiset, but the moment you apply it, of course, on your path, you can actually trace the directions, and they have some nice interplays between the reversal and the complement. Another thing I'm doing here is that these underlining indicate when I am sort of like moving over 0. Moving over 0, let me go back for a second, is cases like when we do this 1 to 5. We think of this as like moving over 0 because we count it as a 3 edge and not as a 4 edge. Every time this happens, we think of our realizations as cyclical realizations because we're taking advantage of the cyclical property of our underlying group. But in some cases, especially if you translate it and if you're lucky, you might get those where you don't actually have to take advantage of the cyclical nature of the group. In those cases, we call our realizations linear. Moreover, if we have a linear realizations that we can anchor at 0, it starts at 0, we call it a standard linear realization. Okay? So as you can see, in each 4 cases, we have linear realizations. And in some of them, I believe in only one of them in this particular case, we end up getting a standard linear realization. Now, as I said, we were given a multiset and we pick these directed edge labels and build our path. But actually, with this multiset, you can pick a different directed edge labels, and then you would come up with another realization. And then this guy in here, in return, would build up. One second, let me move this up. Would build up to 28 other paths all of a sudden. For this example, in this corner, I picked a different realization to show you that for some realizations, it is possible to come up with standard linear realizations that start at 0 and end at the higher index. These guys are very useful because it is possible to add them end to end and use them as building blocks, as like Lego blocks almost. And because of that, they are in the literature called perfect linear realizations. All right, so having established this terminology without belaboring it, we move on to our main result from 2023. What we have achieved is we were able to construct standard linear realizations for these types of multisets whenever A was at least as large as the larger element. Okay, and using those as you'll see, we were able to show that the coprime BHR conjecture holds when V is large enough. Now, the theorem actually follows by very straightforward modular arithmetic once you have this construction. I'll highlight that with just one example. It's very simple following the example. Let's say they've given me this multiset, this underlying set, U1, 7, 8. 7 and 8 are differing by 1, as is our requirement. And let's say RV is 101. So I'm in, the complete graph of size 101, or you can think of it as, Z101, whichever way you like thinking about it. Now, in the cyclic group, automorphisms are given by multiplications, of course. And in mode 101, inverse of 7 is 29, inverse of 8 is 38. So if I multiply this by 29, then 7 will end up becoming 1, and I'll get an equivalent underlying set. Oh, look, and it becomes 1, 29, 30. 29 and 30 are again differing by 1. Very good. If I multiply by 38, so that 8 disappears in a sense into 1. So 8 can be made into a 1 edge. Then I get 38 and 64 doesn't look nice, but then we realize, wait, 64 is actually larger than half of V. So it actually is 37. Oh, and 37 and 38 are also differing by 1. So I get these 3 equivalent multisets. Each of them are of the form 1 x plus 1. Now let's go back for a second to remember this says that this can be constructed as long as A is greater than or equal to the largest one, right? So I can construct this as long as A is greater than or equal to A. I can construct this as long as B is greater than or equal to 30. This as long as C is greater than or equal to 30. So a counterexample would necessarily need to have all of them less. So it would need to have A plus B plus C less than 76. But this needs to be a Hamiltonian path. It needs to span the complete graph. So it cannot be of any length less than V minus 1 and still span V. So it needs to have length 100, but this condition tells me that it needs to be 76 in order for there to be a counterexample. And hence, a counterexample cannot exist. And hence, the BHR conjecture holds as long as V is large enough. All right? So unfortunately, of course, when the difference is not 1, we're not this lucky. But even in those cases, there are certain situations where we can take advantage of those situations and come up with similar results. But again, for the purpose of this talk, I will not delve too much into this. Instead, what I will do next is, let me move this up. I will move to the constructions in the remaining time that I have. And this is, of course, the crux of the matter. And I would really like to spend more time than maybe like about 20 minutes on these, but so be it. Here I'm borrowing a figure from actually another paper, and this link is a active hyperlink. So if the slides get posted online, you can click on it and find it. But what is very important in this is, if you remember, once a multiset is given to us, we don't have to consider ourselves in the complete graph anymore. We can think of ourselves as in the circulant graph, and circulant graphs come with associated toroidal lattices. So that's our topological tool one. I believe everyone in the audience is familiar with how a torus can be built by taking the plane, identifying any two edges, opposite edges of a parallelogram, and gluing and pasting, and the tilings would look like this, and the distance measurements of a flat torus would look like this. The important thing for us is, especially when the underlying set is of size greater than 2, we get actually hypertoroidal lattices. But when the underlying set is only of size 2, we get genuine flat torus lattices. For instance, here, Costa et al. Have this beautiful graph where they have the circulant graph with 13 points, or Z13 underlying group, and with the step lengths 1 and 5. And then they show us how this would correspond to a lattice on the torus, where these edges and these edges are identified. And of course, if you take that lattice and if you tessellate your plane with that lattice, then you have a planar lattice that is, of course, in modulo 13 in some way, but that is very useful to us. That is what we use. All right, so we have started making use of this first through the lenses of, as you can see, because when the underlying set only has 2 elements, especially one of them 1, 1, 5, it becomes very nice, this tessellation. So we started looking at the same problem But we said, can we use these tools to figure out the smallest possible number of one edges, like definitively the smallest possible number of one edges that we would need for a standard linear realization, not the cyclical one, a linear one and a standard one anchored at 0. This was inspired by some existing constructions in the literature, but they weren't actually interested in minimizing. They were using those for their results, and we looked at them. We were like, wait, we can actually ask this problem, because sometimes thinking more restrictively helps with your problem. And it turns out that yes, this was possible, and it only depends on the Euclidean division of b by x. So, someone gives you b number of x edges, and this is your support. What is the smallest number of one edges? It only depends actually on this Euclidean division. This was interesting. And the method was, just as I have described, we take that lattice, that toroidal lattice, but we don't see it as a toroidal lattice. We tessellate our plane with it, and we look at the resulting grid. Now, I'll use some examples, but I'll have to move rather quickly. I have a sequence of beautiful pictures, but maybe you can look at them if this gets shared as a slideshow later. But I'll use those examples to look at the omega, as we call it, omega for 14. Basically, our x is 14. Our x, we have 14 edges. And I'm sorry, our x is 4. I apologize. The order is correct. But we want 14 4 edges. How many one edges do we need to connect them to make into a standard linear realization? All right, so we start with basically not even a modular tiling of the plane, or the lattice of the plane, where the horizontal edges are differing by 1, +1 in the direction to the right, -1 to the left, and verticals are by 4. But of course, this is not very useful to us. What is more useful is to relabel it modularly. Let me move this on, because our b was given as 14. Our path length is 14. So we'll do it modulo 14. And even this is not immediately useful, and it is redundant in case of linear realizations, because linear realizations in this notation can't really cross tilings vertically. This one is a bit more useful. So when you have linear realizations, you're actually all of a sudden just restricted to this slanted lattice, okay? If on top of that, you want it to be a standard linear realization, meaning it needs to start from the vertex 0, then you're even further limited. If you start from here, you cannot pass this zigzag left path, okay? Now, in this visual, I am sort of like switching roles. It's almost like a dual lattice. Of course, these are representing nodes, vertices, and these are representing edges. But I'm showing it like this because what we're really doing is almost like playing in, our cell phones, a snake game. So I wanted to show it this way to highlight the snake game that we're playing. It is actually that elementary, and it's a sort of like an elementary puzzle solving. But on this side, we're limited by this zigzag or zigzagging path. And on this edge or below, we're limited by this. So all of a sudden, we're actually really limited only by this region. All our standard paths are gonna have to be some playing of a snake game inside in here, where the goal of the snake is, of course, to attain all the vertex indices and only once, right? All right, so let's say we start building our path from 0 to I move to 4, from 5 I move 4 to I move 5, from 5 I move to 9. As soon as I hit 9, as you can see, I have like choices. The moment I move right, I'll be in this dark orange region, which I will never be able to leave. Or if I move up or to the left, I'll be in the yellow region, which I won't be able to leave. And either way, because I have already covered 9, I won't be able to reach these areas anymore. So as you keep moving, you're actually at the same time sort of like eating out all the other areas that you can reach. So you're getting very, very restrictive. But we have another thing that we are interested in. Oh, let me actually show you one example here. This is one example of a standard linear realization, but you can see that this is by no means minimal in A, because here's a one edge, here's a one edge, one edge, one edge, one edge, one edge, way too many one edges. But if we want to minimize the one edges, then of course it is in our interest to maximize the four edges, so to maximize vertical moves, meaning that these things that we lovingly call facets, they are not honest cosets, but once you like limit your region to this, they or act like cosets. So it is in my interest to try to like cover this in one go, and then from this move on to the next one, right? So I either like start from 0 and go all the way to 12 with 4 steps, 4 steps, and from 12 I either move to 13 or to 11, right? Here is one way of minimizing, by the way, in a non-standard way. But again, we're interested in standard. So either I'll start and I'll restrict myself to the right, or I'll start and I'll restrict myself to the left. If I restrict myself to the left, once I hit the vertex 9, I'm in a bit of a difficulty. I've already covered every place that I can go. I cannot attain these values anymore because I've already attained them. I either turn right or up and I miss these guys, or I turn down and I miss this guy. So that won't be a Hamiltonian path. But if I do it in the other direction, I get a Hamiltonian path. And I do get a Hamiltonian path with only 3 one steps. So omega of 414 is 3, meaning if someone gives me an underlying set made out of step lengths of 1 and 4, and they say that they want its length to be 14, then I can achieve this with at most, or at least actually, at least 3 one steps. And it won't get better than this because I have these 4 facets that I need to connect, and I will need to use 3 one steps to connect them. It cannot be better than this. All right, so based on the Euclidean division, we get 2 results. In this one particular case, the omega becomes exactly the same as x. In most cases, it's x minus 1. Let me go back up again. This is x minus 1. I needed only 3 of them to connect the 4 facets. But in this one case, I cannot do that because I need what we call a tail curl. They will become clear when I show you the pictures. And for the specialist, these, of course, give us what's called growable realizations. That will also become clear as soon as I show the next picture. All right, next picture. So this is what growable means. These constructions that we have, they can be extended up and extended down by adding multiples of your x. And the constructions depend on the parity of x and r. When x is odd and r is even, or when x is odd and r greater than 1 is odd, we have actually 2 different choices. And sometimes they come in handy. But this is basically the picture that shows us standard linear realizations with minimal a based on different parities. And this is the problematic one. In this case, if you do the snake game, you notice that one of the facets need to be visited twice. So I need to go back and trace back, which we call a tail curl. And that gives me that additional 1 step that I need to take. In all of the others, I can move between the facets by just 1 step. But here I have to do 2 one steps here, or here I have to do 2 one steps here. And in certain cases, instead of following the general pattern, we sometimes consider these like special cases that don't really fit into the picture, but they come in very handy when we're dealing with edge cases. All right, I'll move on beyond this because I'm fast running out of time. And I'm also coming to the areas where these are like relatively recent things that we discovered. This is, for instance, something that we discovered just in February. So you'll have to deal with my handwritten notes in here. This is our second topological tool, and it comes from branched covers and liftings of branched covers, if you could believe. Early on, even before 23, we had noticed that we were getting these very nice perfect linear realizations for instance, x and x plus 1. This would be like, 3 steps and 2 steps, or this would be 4 2 steps and 1 3 step. And then we also later realized that this wasn't just restricted to x and x plus 1. it was happening every time X and Y were co-prime, but we were a bit confused as to what the underlying structure would be. Later, we realized that these were connected to one another via this bridging Hamiltonian cycle in between, not a path, but a cycle in between. That, of course, opened up a whole can of worms. So once we started analyzing it, we realized that the Hamiltonian cycle that we were getting was actually a cycle that was coming from a generating element of the group that was viewed linearly. So for instance, if you have all 5 steps cyclically, but you want to think of it linearly, then all 2 steps, 2 of those 2 steps, you see them as 3 steps instead of 2 steps, because, when you're thinking of them linearly, you don't think of like jumping over the 0 anymore. And those 2 are exactly what your generating element was. Because X is 2 in this case, there will be 2 times that I will be taking advantage of the cyclicity. And those I see as 3 steps if I look at them linearly. So the thing that we realized, let me move the menu out of the way, is that basically this is all coming from how the interval forms a branched cover of the circle. Okay? And again, here, this is why I had initially mentioned that view with the nth roots of unity, because now it will be in my best interest to think of my vertices as nth roots of unity on this circle and consider what happens when I look at the liftings via this branched cover of my circle into these intervals. The interesting thing that happens is this cycle lifts exactly to those perfect linear realizations that we were noticing. So basically, a Hamiltonian cycle in the circle gives you 2 perfect linear realizations, because in this branch cover, there are exactly 2 lifts. One lift is where, 0 moves up to 0. The other is where 0 moves up to, if you want to consider it like in unit length interval 1. If you want to consider that like a 2 pi length, arc interval to 2 pi, right? So this means that these actually are core perfect realizations, core perfect linear realizations. All other perfect linear realizations can be described in terms of these guys via a game of snake built upon these. And these are minimal. One of them is minimal. If I go back, one of them is minimal in terms of the number of x's it contains. The other one is minimal in terms of the number of y's it contains. And they become very useful to us. Again, I apologize for having to pass this quickly because I'm running fast out of time. But basically what that means for us is that when you have co-prime x and y, you have these perfect realizations. Well, x and x prime, x plus 1 are always co-prime, so you have these perfect realizations. If you sort of like interlace these perfect realizations, which can be called a spanning linear forest, then you have these other corollaries, which I won't dig into because I'm running fast out of time. Now, what we do is we take those minimal omega constructions, as we call them, with that earlier snake game, and we take these perfect realizations, and now comes the third topological tool, thinking of these as paths and thinking of their concatenations. So by concatenating these, we can use these as building blocks and build a bigger path. Now, I won't get too much into the details of this. Instead, I'll sort of like show it to you via pictures because I'm running out of time. But one thing that's important is because the multiset that consists of only ones has always this perfect realization, you can always increase the number of ones in your set by just like adding that path of ones at the end, okay? Which you will see in a moment. So this brings us to the next construction tool, which is taking those optimal constructions and modifying them, combined with this concatenation idea. Once again, instead of going through the word salad in here, I'll show it to you via these pictures that I think is gonna describe it very well. For instance, let's say we want to construct a 3-element multiset with 1, 7, and 8 as the underlying set. They want 18 copies of 7s and 32 steps of size 8. And we're trying to figure out Well, how few ones can I use in this case? Well, I already know that I don't need to worry about these big numbers because I have these perfect realizations of 7 copies of 7 and 8 copies of 8. So that already reduces what I need to look at to only 4 copies of 7 and 16 copies of 8. So those guys mean that I can focus on sort of like this picture. And when I don't even look at this picture, that picture, but instead I say ignore the 7s because 16 is greater than 4. What if they were all 8s? I build the minimal construction assuming that they were all 8s. And then we have observed that there are these beautiful moves where you can just switch up to, let's call it X many X's, either in pairs or sometimes in odd values, and come up with the desired a path that has the desired multiset that's realizing the desired multiset. So the first example that I have shows a case where after the reduction we get sort of like an even with an even remainder. This is after the reduction an odd with an even remainder, and here we need to actually do modifications of odd number of edges, but it is doable because of this move that we lovingly call a corner cut. So by doing that corner cut, we're able to also manipulate odd numbers of them. In the next page, I'll show more examples. In these cases, when we do the reduction, it turns out that the multiplicity of the smaller one is higher than the larger one. So we say, okay, don't think about the 8s. Assume that everything was 7s and build it as if everything was 7s, and then do those manipulations to come up with the 8 edges. And again, we can do it for even numbers of them, but we can also do them for odd numbers of them thanks to this move that we lovingly call a corner flap. So seeing all of these, what we get is we get basically multiple things that we have used. We have perfect realizations combined with these like optimal constructions for only 2 elements, but then those optimal constructions are also modified to add a third element to the picture. And then, as I said, if you want higher number of ones, you can always add this dummy path of ones at the very beginning, prepend as we call it. All right, so that is one strategy. But after publishing our paper, we become aware that there is actually, especially in this particular case, another strategy available. In this strategy, instead of doing all of this concatenation, you take these blocks, you take these optimal constructions, and you make modifications blockwise in blocks of 4. Now, of course, blocks of 4 would not be enough, but then at the very top row, I can do modifications in blocks of 2, or if need be, I can do modifications by a corner cut or a corner flap, covering all the odd cases also. Now, this is a generalization of what we've observed is called this move, this like changing 4 of them in a 4 block, is called a transposition in a dissertation that we found in the field of electrical engineering. So that made us aware that grid graphs have actually applications in electrical engineering. So these questions that we're asking and these sort of like correspondences that we have noticed between the Buratti-Horak-Rosa conjecture and grid graphs also have in return then applications in electrical engineering. So there we go. That's like, maybe something like a train schedule kind of industrial engineering problem, or a computer science problem through graph decompositions, or maybe an electrical engineering problem through looking at grid graphs. So this problem has a lot of potential to be applicable to many fields. All right, so in the very little time that I have left, I'll just mainly tell you what happened since these results. Recently, what we have done is, what I've shown you was the difference between y and x was only 1. But we were able to do this in the very last paper that we have submitted for also difference being 2. And after that paper was submitted just past month, we were able to do something similar for the difference being 3, but in that case, our bound is a bit higher because we can't use perfect realizations anymore. We have to do something else. And I'll show you that something else. That something else is these interlaced perfect realizations. I won't be able to do this any justice, but if you look at this, this is very similar to those other pictures. The ones are not at the end, but in the middle, because these are not perfect anymore. They are standard. So hence the ending result is also not standard, but just linear. And these are similar moves as the moves with slanted 1 edges, but they are now slanted basically y minus 2 edges. And before I end, what I'll tell you is that these give us hope that we can, using concatenations, come up with this bound for general x and y, or without concatenations for using inner block moves, but maybe for k not large enough, we can come up with a better bound. This would give us a weaker bound, but it's the easier problem. This would give us a stronger bound, but it is by far a harder problem.